Hello and welcome to 8.7, the indeterminate forms and L'Hopital's rule. Okay, indeterminate forms where when a limit is 0 over 0 or infinity over infinity. A lot of people want to call that 1, and we really can't do that. It's indeterminate, it's not known. This is undefined, so is this. Now it could turn out that it is 1, or it could be 0, or it could be infinity. So we look at case by case, and we're going to learn these tools now. So recall from Calculus 1, the limits. If you take the limit as x goes -1 of 3x squared minus 3 over x plus 1, you're going to get 0 over 0. And if you do the limit as x goes to infinity of 3x cubed plus 2 over 2x cubed plus 1, you get infinity over infinity. So in the first case, if we factor out at x plus 1, we would see that the limit's -6. In the second case, if we divide it by x cubed on the numerator and denominator, we get 3/2. We're going to learn a tool to find this limit using a little shorter process. Okay, so theorem 8.3, extended mean value theorem. If f and g are differentiable on an open interval from a to b and continuous on the interval from a to b, such that g of x is not equal to 0 for any x in a, b, then there exists a point c in a, b such that f prime at c over g prime at c is equal to f of b minus f of a over g of b minus g of a. And we have L'Hopital's rule says, let f and g be functions that are differentiable on an open interval from a to b containing c except possibly at c itself. Assume that g prime of x is not equal to 0 for all x in the interval from a to b except possibly at c itself. If the limit of f of x over g of x as x approaches c produces the indeterminate form 0 over 0, infinity over infinity, negative infinity over infinity, infinity over negative infinity, or negative infinity over infinity, we covered pretty much all those cases there, didn't we? Then here's this cool thing, and this should be limit as it approaches c. Limit as x approaches c of f of x over g of x is the limit as x approaches c of f prime of x over g prime of x. So you take the derivative of the numerator and the derivative of the denominator and you evaluate it. If it's still indeterminate, you can take it again and again until you get something that is determinate. So provided the limit exists. So evaluate with and without L'Hopital's rule the limit as x approaches 3 of 2 times x minus 3 over x squared minus 9. So with L'Hopital's rule, you have the limit as x approaches 3 of 2 times the quantity x minus 3 over x squared minus 9 is the limit as x approaches 3. Now the derivative of the numerator is just going to be 2. And the derivative of the denominator is going to be 2x. As x approaches 3, that's 2 over 6, which is 1/3. So that's the limit as x approaches 3. Without L'Hopital's rule, we have the limit as x approaches 3 of 2 times the quantity x minus 3 over x squared minus 9 is the limit as x approaches 3 of 2 times x minus 3 over x minus 3 times x plus 3. So the x minus 3's divide out. This gives us the limit as x approaches 3 of 2 over x plus 3, 2 over 3 plus 3, 2 over 6, which is 1/3. Look at that, same thing. Not a surprise though, that's what we should have had. Okay, so L'Hopital's rule. Now, don't use L'Hopital's rule if it's not in the indeterminate form, because you're going to have problems. This is for being in the indeterminate form. Okay, going on to the next page. Evaluate the limit as x approaches negative 1 of x squared minus x minus 2 over x plus 1. So by L'Hopital's rule, that's going to be 2x minus 1 over just 1. So now if I plug in the negative 1, it's going to be 2 times negative 1 minus 1 over 1. That's negative 2 minus 1 over 1, negative 3 over 1, which is negative 3. Boom, that's it. Now I really want to stress though, I took the derivative of the numerator, I took the derivative of the denominator. This is not the quotient rule, this is L'Hopital's rule. You should take those separately. Evaluate the limit as x approaches 0 of sine ax over sine bx. So right now if you put the 0 in there, you're going to have sine of 0 over sine of 0, which is 0 over 0, which is indeterminate. So we're going to have the limit as x approaches 0. Now if we write like an h when we've taken L'Hopital's rule. That's going to be derivative of sine is going to be a cosine of ax over b cosine of bx. If we plug in that 0, we have a cosine of 0 over b cosine of 0. That's a times 1 over b times 1, which is a over b. See? That's not 1, that's not infinity, that's something different. It's kind of cool. Let me scroll this up. Okay, example 4. Limit as x goes to infinity of x cubed over x plus 2. So right now we have infinity over infinity. If we apply L'Hopital's rule, we'll have the limit as x approaches infinity of 3x squared over 1. So now it's not indeterminate anymore, because if you put infinity in there, you're not going to have infinity over infinity. You have 3 times infinity squared over 1, which is just infinity. So that is the final result. I'm going to move on to example 5. Describe the type of indeterminate form that is obtained by direct substitution. Evaluate the limit using L'Hopital's rule, if necessary, and use a graphing utility to graph the function and verify the results. I'm not going to graph it though, but these are directions from the homework part. Okay, so right now, if you plugged in the limit, you're going to have 0 cubed times cotangent of 0, which is 0 times infinity. That's the situation. Now this is also an indeterminate form. 0 times infinity, is it 0, is it infinity, is it 1, is it something else? We don't know. So we're going to use L'Hopital's rule. So think of this as the limit as x approaches 0 from the right side of x cubed over tangent x. Why over tangent? Because cotangent is 1 over tangent. Now if I plugged in the 0, I have 0 over 0. L'Hopital's rule applies. So the limit as x approaches 0 from the right side of 3x squared over, and the derivative of tangent is secant squared x. Now if I plug in that 0, I'm going to have 0 over 1, so it's not indeterminate anymore, so it's 3 times 0 squared over secant squared of 0. That's 0 over 1, which is 0. So check it out. In this case, 0, 1 over infinity. Okay, we're going to go on to the next page, so feel free to pause that. Okay, for this next one, it says describe the type of indeterminate form that is obtained By direct substitution, evaluate the limit using L'Hopital's rule if necessary. Use a graphing utility to graph the function and verify the results. So if the limit as x approaches 2 from the right side of 8 over x squared minus 4 minus x over x minus 2. So if you were to plug in these values and plug in 2, let's see what happens. You'd have 8 over 2 squared, 4 minus 4 minus 2 over 2 minus 2. That's 8 over 0 minus 2 over 0. That's infinity minus infinity. Now what is infinity minus infinity? Is it 0? Is it infinity? Is it something else? I don't know. Let's find out. So that's the case we have. Let's do this. The limit as x goes to 2 from the right side of 8 over x squared minus 4 minus x over x minus 2. See, we could factor this denominator. That'd be the limit as x goes to 2 from the right side of 8 over x minus 2 times x plus 2 minus x over x minus 2. I'm going to multiply the second term by x plus 2 over x plus 2. And this will give us the limit as x goes to 2 from the right side of 8 minus x times x is x squared, x times 2 is 2x, over x minus 2 times x plus 2. So that's going to be the limit as x goes to 2 from the right side of what? Well, right now if I put this 2 in here, 8 minus 4 is 0. 2 minus 2 is 0. So I have 0 over 0. L'Hopital's rule applies. So I'm going to apply L'Hopital's rule. The derivative of the numerator is negative 2x minus 2. And the derivative of the denominator is going to be, it was this originally, 2x. So maybe I should go back and I'm going to do this in another step. I'm going to back it up. We call this limit as x approaches 2 from the right side of negative x squared minus 2x plus 8 over x squared minus 4. And that's going to be applying L'Hopital's rule, the limit as x goes to 2 from the right side of negative 2x minus 2 over 2x. Now if I plug in this 2, I don't have the indeterminate form. So it's going to be negative 2 times 2 minus 2 over 2 times 2. That's negative 4 minus 2 over 4. Negative 6 over 2 over 4, excuse me. Negative 3 halves. Okay, that's it. So it was a little confusing. Oh, what do we do with this negative infinity or infinity minus infinity? What do we do with that? Well, go back and use algebra to make them one term so you have something over something else. Move on to example 7 then. Now this says use a graph utility to graph the function and find the required limit. We're going to do this another way. I can show you some things with the calculator in our lessons, or I can make some more videos for you. We have the limit as x goes to 0 of sine x to the x. So what we're seeing here is sine of 0 to the 0 power. That's like saying 0 to the 0 power. And what is 0 to the 0 power? Is that 1? Is it 0? So we have, treat this like this, y equals sine of x to the x. And one of the tools we commonly use when we deal with exponentials like this is the natural log. So natural log of y equals natural log of sine x to the x. So the natural log of y is going to be x natural log of sine x. Now if we took the limit as x goes to 0 from the right side of x natural log of sine x, what we'd have is 0 times natural log of 0, which is 0 times negative infinity. So we have an indeterminate form. There's no n, there's TE. Okay, we have an indeterminate form. So, applying L'Hopital's rule, treat this as the limit as x goes to 0 from the right side of the natural log of sine x over 1 over x. So this would end up flipping up and become a coefficient. So now we can apply L'Hopital's rule because natural log of sine x is negative infinity, 1 over 0 is infinity. So that's going to be the derivative of natural log of sine x is going to be 1 over sine x times the derivative of sine is cosine x over, this derivative is going to be negative 1 over x squared. So we have the limit as x goes to infinity, or to 0 from the right side, of cotangent x over negative 1 over x squared. Now, what if we wrote this as the limit as x goes to infinity, to 0, 1 over x squared, so this can come up, be negative x squared. Cotangent is the same thing as 1 over tangent x. So cotangent is 1 over tangent. We still have 0 over 0, but now if we take the derivative, do L'Hopital's rule, we have the limit as x goes to 0 from the right side of negative 2x over secant squared x. Putting 0 in there, that's negative 2 times 0 over secant squared of 0 at 0 over 1, which is 0. Not finished though. That is saying natural log of y equals 0. So those of you who thought, yeah, 0 to the 0 is 0. Watch this. I mean, that's a case-by-case situation. In this case, watch what happens. Natural log of y is 0. E to the natural log of y is e to the 0. So y equals e to the 0, which is 1. Therefore, the limit as x approaches 0 from the right side of sine of x to the x power is 1. And the graph of that looks like this. And there's 1. Whew, that was an involved problem. Okay, we've got 2 problems left to go for this section. Clear the board. So let's use L'Hopital's rule to determine the comparative rates of increase of the functions. F of x equals x to the m, g of x equals e to the nx, h of x equals natural log of x to the n, where n is positive, m is positive, and x goes to infinity. So the one we're working with is the f and the g, where the limit is x goes to infinity of of x cubed over e to the 2x. So which one's growing faster? We can take, right now, put infinity in there, you have infinity over infinity. So if we take L'Hopital's rule, we have the limit as x goes to infinity of 3x squared over 2e to the 2x. So plugging in infinity now, you're still going to have infinity over infinity. Take L'Hopital's rule again. That's going to be the limit as x goes to infinity of 6x over 4e to the 2x. Plug in infinity, we still have the indeterminate form of infinity over infinity. And taking L'Hopital's rule again, the limit as x goes to infinity of 6 over 8e to the 2x. Now if we plug in infinity of 6 over infinity, that's just 0. So what this is saying is that e to the 2x grows faster than x to the third power. In fact, e to any power, exponential I say, with a variable in the power, is going to grow faster than x to any power, as long as m is a real number. Okay, this last one, example 9, it says, L'Hopital's rule is used incorrectly. Describe the error. Okay, so if you look at this, we have the limit as x goes to 0 of e to the 2x minus 1 over e to the 2x. Then they come to 2e to the 2x over e to the x. That reduced to be 2e to the x, which is 2. Well, what's the problem with this? If you put in 0, what we have is e to the 2 times 0 is 1, e to the 1. Sorry, e to the 2 times 0 is 0, e to the 0 is 1. So we have 1 minus 1, that's 0 on top. But e to the 0 is 1. So you have 0 over 1. This is not indeterminate. The limit as x goes to 0 of e to the 2x minus 1 over e to the x is e to the 2 times 0 minus 1 over e to the 0. That's 1 minus 1 over 1. That's 0 over 1, so it's 0. This is not indeterminate. That's it. Okay. And that'll do it for 8.7, L'Hopital's rule. I think it's kind of a fun section. So send me your questions, and I'll see you guys when we meet together as a class. Thank you.